A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
Imagine for a second that you are standing at the bottom of a swimming pool. You can feel that slight pressure in your ears, right? That is just a few feet of water. Now, imagine diving down to 12,500 feet. At that depth, the water is pressing in on you with about 5,800 pounds of force on every single square inch of your body. That is roughly 400 times the atmospheric pressure we feel at sea level. To visualize that, it is like having the weight of an African elephant concentrated onto a postage stamp, and then tiling your entire body with those stamps. And then, in less than 2 milliseconds, faster than the human brain can even register a pain signal, the walls around you simply cease to exist.
Herman Poppleberry here, and that is not hyperbole. When we talk about the Titan submersible implosion that happened back in June of 2023, we are talking about a physical event so violent and so fast that it transcends our normal understanding of a crash. This was an adiabatic compression event. The air inside the hull was compressed so instantly that it briefly reached temperatures approaching the surface of the sun. But the real tragedy, Corn, and what our housemate Daniel was getting at when he sent over this prompt, is that this was not some freak act of nature or an unforeseeable accident. This was a forensic engineering disaster that was essentially written into the blueprints of the vessel years before it ever touched the water. It was a collision between a specific type of corporate hubris and the immutable, unforgiving laws of fluid dynamics.
It really was. And I think that is what makes this topic so haunting for people who understand engineering. It was not a mystery. It was a slow-motion train wreck involving the move fast and break things ethos of Silicon Valley being applied to a domain where breaking things means people die. Daniel wanted us to really tear into the technical side of this. And honestly, I've been wanting to do this deep dive for a while. Because while the headlines focused on the surge and the drama of the oxygen timer, the real story was already over. The story is in the material science, the geometry of the hull, and a systemic rejection of a safety culture that has kept deep-sea exploration remarkably safe for over half a century.
To understand why the Titan failed, you first have to understand why every other deep-sea vehicle succeeds. If you look at the history of deep ocean exploration, from the bathyscaphe Trieste in 1960 to the Alvin or Victor Vescovo's DSV limiting factor, they all share a common DNA. They use spherical pressure hulls made of high-strength metallic alloys, usually titanium or specialty steel. Why a sphere? Because a sphere is the only shape that distributes external pressure equally across its entire surface. There are no corners, no weak points, no flat spots that want to buckle. And why metal? Because metals like titanium are isotropic. That means they have the same physical properties in every direction. When you squeeze a titanium sphere, it shrinks uniformly. It is predictable. It handles the stress the same way every time.
Right. And the Titan was the complete opposite of that established wisdom. It was a cylinder, not a sphere, and it was made primarily of carbon fiber. Now, for the average person, carbon fiber sounds like the ultimate high-tech material. We see it in Formula One cars, high-end bicycles, and the latest Boeing Dreamliner wings. It is incredibly strong for its weight. But there is a massive catch that Stockton Rush, the CEO of OceanGate, seemed to treat as a secondary concern. Carbon fiber is an anisotropic material. Its strength is directional. It is designed to be incredibly strong in tension, meaning when you are trying to pull it apart. But it behaves fundamentally differently when you put it under compression, especially the kind of massive cyclic hydrostatic compression you get at the bottom of the Atlantic.
That is the core of the failure, Corn. Let's get into the weeds on the carbon fiber hull. Carbon fiber is what we call a composite material. It is made of thousands of tiny carbon filaments held together by a polymer resin, usually an epoxy. When you build an airplane wing out of it, you are taking advantage of the fact that as the wing lifts, the fibers are being pulled tight. They are in tension. They are like tiny, incredibly strong cables. But a submersible hull is the exact opposite. The water is trying to crush that cylinder inward. It is in pure compression. In this state, the carbon fibers aren't the primary heroes anymore. The resin holding them together has to do a massive amount of the work to keep those fibers from buckling.
And here is the problem with composites in compression. They suffer from something called delamination. Imagine a thick stack of paper. If you pull on the ends of the stack, it is quite strong. But if you try to stand that stack of paper on its edge and push down on it, the individual pages start to buckle and slide past each other. They unzip. In a carbon fiber hull, every time that vessel dived, the massive pressure was squeezing those layers together, but it was also creating tiny microscopic imperfections. Maybe a tiny air bubble in the resin, or a place where the fibers were not perfectly aligned during the winding process. Every dive was a cycle that stressed those imperfections.
This brings us to the concept of fatigue, which we have touched on before. Back in episode 771, when we talked about critical redundancy, we discussed how systems fail when they are pushed past their design limits repeatedly. With the Titan, they were using a material that does not handle fatigue the way titanium does. Titanium is ductile. It will often show signs of stress. It will microscopically deform or creep in a way that can be measured before it fails. Carbon fiber is brittle. It does not bend. It does not give you a warning by deforming. It just shatters. It is a binary material. It is either holding or it is dust.
It is the difference between a soda can and a glass bottle. If you step on an empty soda can, it dents and crumples. It absorbs energy through deformation. If you step on a glass bottle, it holds its shape perfectly until the exact moment it reaches its breaking point, and then it explodes into 1,000 pieces. Stockton Rush actually bragged about the fact that the Titan's hull would make cracking and popping sounds as it descended. He claimed this was part of a high-tech acoustic monitoring system that would warn the pilot if the hull was about to fail. He called it the real-time hull health monitoring system.
Which, from a forensic engineering standpoint, is absolutely terrifying. If you are hearing the fibers in your primary pressure hull snapping, you are not receiving a warning. You are listening to the sound of your vessel dying in real time. By the time those acoustic sensors picked up enough noise to trigger an alarm, the structural integrity was already compromised. You are at 12,000 feet. You cannot just hit an emergency brake and be safe. It takes hours to surface. It was a reactive safety system in an environment that requires proactive structural certainty. It is like saying your car has a safety feature that tells you the brakes have failed after you have already driven off the cliff.
And let's talk about that geometry again. Why a cylinder? We mentioned that every other deep-sea submersible uses a sphere. OceanGate wanted to carry 5 people to make the economics of the tourism work, $250,000 a head. To fit 5 people in a sphere, the sphere would have to be enormous, which makes it incredibly heavy and difficult to launch, so they went with a cylinder to increase the internal volume. But a cylinder is inherently weaker under pressure. It experiences what we call hoop stress. The middle of that cylinder wants to flatten out, or egg. To compensate for that, they had to make the carbon fiber walls 5 inches thick. But then you run into the problem of the joints. You have this massive carbon fiber tube, and then you have to cap the ends with something. They use titanium hemispherical end caps.
This is where the physics gets even more treacherous. This is the interface problem. You are joining 2 completely different materials with 2 completely different elasticities. You have carbon fiber and you have titanium. They have different values for something called the Young's modulus, which measures how much a material deforms under stress. When the Titan went down to nearly 4,000 meters, the titanium caps and the carbon fiber hull were shrinking at different rates. They were fighting each other at the seam.
They were bonded together with a specialized glue, a high-strength epoxy. But as the hull squeezed in, that bond was under incredible shear stress. Imagine trying to glue a piece of rubber to a piece of wood, and then twisting them in opposite directions while pushing them together. Eventually, the glue or the interface layer of the composite is going to give way. Most forensic analysts, including those who have looked at the recovered debris, believe the failure likely started at one of these interfaces. A tiny gap opens up. A jet of water at 6,000 pounds per square inch shoots in like a laser cutter, and because the carbon fiber is brittle and already fatigued from previous dives, the whole thing just disintegrates.
And we have to address the experimental label that Rush used as a shield. In the maritime world, there are organizations like the American Bureau of Shipping, or ABS, and DNV in Norway. These are called classification societies. They are the independent third parties that review every single calculation, inspect every weld, and oversee every pressure test of a new vessel. They ensure there is a factor of safety. In professional deep-sea engineering, you typically have a factor of safety of at least 1.5. That means if you are diving to 4,000 meters, the hull is designed and tested to withstand the pressure of at least 6,000 meters. You want that buffer because you know that materials have imperfections and that the ocean is unpredictable.
And Stockton Rush famously refused to have the Titan classed. He wrote a blog post about it in 2019, saying that certification stifled innovation. He argued that because the Titan was so experimental, the existing regulations did not apply, and that the certification process was too slow for his pace of development. He essentially said, "I know more than the collective wisdom of the last 80 years of ocean engineering."
Which is a fundamental misunderstanding of what engineering certification is for. Certification isn't there to stop you from being creative. It is there to ensure that your creativity doesn't kill people. When you are building a bridge or a skyscraper or a deep-sea submersible, you don't get to just move fast and break things, because the things you are breaking are human lives. The marine technology community saw this coming a mile away. In March of 2018, the Marine Technology Society sent a letter to Rush, signed by dozens of the world's leading deep-sea experts, warning him that his experimental approach could lead to a catastrophic event.
I remember reading that letter. It was chillingly accurate. They specifically pointed out that the marketing for OceanGate was misleading because it claimed the vessel would meet or exceed various standards, even though they had no intention of actually undergoing the third-party testing required to prove it. They were essentially grading their own homework, and when someone within the company tried to raise the alarm, the response was not, "Let's check the math." It was, "You're fired."
You're talking about David Lockridge. He was the director of marine operations at OceanGate. He was a veteran sub-pilot. In 2018, he wrote a scathing quality control report stating that the hull had not been properly tested. He wanted non-destructive testing, like ultrasonic scans, to check for voids or delamination in the carbon fiber. OceanGate told him that the hull was too thick for those scans to work, which is a massive red flag. If you can't test your material for internal flaws, you shouldn't be using it for a life-critical system. Instead of listening to Lockridge, they fired him and sued him for disclosing confidential information. That is the definition of a broken safety culture.
It really is. And it's not like the industry didn't have a roadmap for how to do this safely. Look at Triton submarines. They built the limiting factor, which Victor Vescovo used to reach the bottom of the Mariana Trench, nearly 11,000 meters down. That sub is fully classed by DNV. It went through years of rigorous testing. They tested the hull in pressure chambers to pressures far beyond what it would ever see in the ocean. They did non-destructive testing, ultrasound, x-rays, everything. They proved it was safe before they ever put a person inside.
And that is the difference. Triton spent the money and the time to prove their design was safe. Stockton Rush seemed to view those costs as an obstacle to his vision of making the Titanic accessible to wealthy tourists. It was a classic case of hubris. He believed that because he had successfully dived a few times, he had beaten the physics. But the ocean doesn't care about your past successes. Every dive is a new test, and with a fatigued carbon fiber hull, the odds of failure were increasing with every single trip. This is what engineers call the normalization of deviance. It's a term coined after the Challenger disaster. You do something risky, it doesn't fail, so you assume the risk isn't there. You keep doing it until the deviance becomes your normal, and then the math finally catches up with you.
That normalization of deviance is so relevant here. They had signs of trouble early on. There are reports that the hull they actually used for the final missions was actually a second version, because the first one had already shown signs of fatigue after just a few test dives. They knew the material was degrading, but they convinced themselves that the acoustic monitoring system would save them. It's like driving a car where the engine redlines at 60 miles per hour, and you are trying to drive 60 miles per hour for hours at a time, relying on a sensor to tell you the engine is about to explode. Eventually, something is going to snap.
You know, it reminds me of our discussion in episode 8014 about the carrier strike group. When you look at military-grade engineering, like the USS Gerald R. Ford, the level of redundancy and the strict adherence to protocol is what keeps those massive systems functioning in hostile environments. There is a culture of total accountability. In the Titan's case, it was a cult of personality. Rush was the CEO, the lead designer, and the chief pilot. There was no one with the authority to tell him no. He had surrounded himself with young, eager engineers who didn't have the decades of experience to know why the old ways of using titanium spheres were there in the first place.
He famously said in an interview that he didn't want to hire 50-year-old white guys with experience because they weren't inspirational. But in engineering, experience is just another word for, I have seen how things fail. You want the person who has seen a hull buckle. You want the person who understands why we don't use carbon fiber and compression. Innovation is great, but you have to innovate from a foundation of understanding, not from a foundation of dismissal.
Let's look at the broader landscape of undersea tourism for a second, because I don't want people to think that the entire industry is this reckless. It is actually a very small and very professional community. Most of the submersibles used for tourism are what we call shallow water subs. They go down to maybe 100 or 200 feet. They are basically glass-bottom boats that can submerge. They are heavily regulated and very safe. They operate in the territorial waters of countries like the Bahamas or Mexico, where they have to follow local laws.
Right, but the deep-sea tourism market, the really deep stuff that was almost non-existent outside of OceanGate, most deep-sea exploration is done by government agencies or academic institutions using ROVs, which are remotely operated vehicles. They don't put people inside. If an ROV implodes, you lose some expensive equipment, but everyone goes home for dinner. Stockton Rush was trying to create a market where there wasn't one, and he was doing it by exploiting a regulatory loophole. Because they were operating in international waters, they weren't subject to the laws of any specific country. They launched from a Canadian-flagged ship, but the sub itself was essentially a stateless vessel.
There are only a handful of human-occupied vehicles in the world that can reach the depth of the Titanic. You have the Alvin, which is operated by the Woods Hole Oceanographic Institution. You have the French Nautilus and the Russian Mir subs, which were actually used by James Cameron when he was filming the Titanic movie. All of those vessels were built to incredibly high standards and are maintained by teams of world-class engineers. And notice something? They are all spheres. They are all metal or, in some cases, specialty syntactic foam for buoyancy. None of them use carbon fiber for the pressure hull.
And James Cameron himself is a perfect example of how to do this right. When he built the deep-sea Challenger to go to the bottom of the Mariana Trench, he spent years on the engineering. He worked with the best experts in the world. He didn't just throw some carbon fiber together and hope for the best. He respected the pressure. He actually spoke out after the Titan incident, saying that he felt the similarity to the Titanic disaster itself was striking, where the captain was repeatedly warned about ice ahead, and yet steamed full speed into an ice field on a moonless night.
I think that is the key phrase, respecting the pressure. You cannot bargain with the deep ocean. It is a world of pure physics. If you have a 1% weakness in your design, the ocean will find it. And it won't just find it, it will exploit it instantly. The Titan was a series of 1% weaknesses: the cylindrical shape, the carbon fiber material, the mismatched titanium interfaces, the uncertified viewport, that all added up to 100% certainty of failure over time.
So, let's talk about the takeaways here. For our listeners who are in engineering or any kind of technical field, what is the lesson of the Titan? To me, it is the importance of peer review and independent verification. You can be the smartest person in the room, but you still have blind spots. You need someone else to look at your work and try to find the flaws. In engineering, trust me is not a valid data point.
And you have to understand the difference between innovation and corner cutting. Innovation is finding a better, safer, or more efficient way to do something within the bounds of physical reality. Corner cutting is just ignoring the rules because they are inconvenient. Using carbon fiber for a deep-sea pressure hull wasn't innovation. It was a mistake that had been proven to be a mistake decades ago. In the 1980s, the Navy looked at composite hulls and realized the delamination issues were too great for repeated deep dives. Rush didn't discover something new, he just ignored something old.
I also think it is a lesson in how to evaluate disruptive companies. We see this a lot in the tech world. A company comes in and says the old way of doing things is obsolete and that they have a new, revolutionary approach. And sometimes that is true. But when that disruption involves life safety systems, you have to be incredibly skeptical. If they are refusing to undergo standard industry certification, you have to ask why. Is it really because the process is too slow? Or is it because they know their design won't pass?
It is almost always the latter. Certification is a high bar, but it is a necessary one. If you can't prove to an independent board of experts that your submersible is safe, then you shouldn't be putting people in it. Period. The fact that OceanGate was able to operate for as long as they did is a testament to the lack of international regulation on the high seas. I suspect we will see new international agreements to regulate private submersibles, similar to how the FAA regulates the aerospace industry. You can't just build a plane in your backyard and start selling tickets to fly people across the country. You have to prove the plane is airworthy. We need the same thing for seaworthiness in the deep ocean.
And it's not just about the regulations, it's about the engineering ethics. As an engineer, your first responsibility is to the public. You have a duty to speak up if you see something that is unsafe. The story of David Lockridge is a tragic one, because he did exactly what an engineer is supposed to do, and he was crushed for it by the company. We need to create environments where safety concerns are taken seriously, not treated as a threat to the mission.
It really comes down to redundancy versus reliability. We talked about this in episode 771. Redundancy is having a backup system in case the first one fails. But redundancy is useless if the primary structural design is fundamentally flawed. You can have all the acoustic sensors and backup weights in the world, but if your hull shatters, none of that matters. Reliability is about the core integrity of the system. You build reliability through proven materials, conservative design, and rigorous testing. You don't build it through marketing and experimental labels.
Well said, Herman. This has been a heavy one, but I think it is an important conversation to have. Engineering failure is rarely just about a single bolt or a single weld. It is about a chain of decisions and a culture that allows those decisions to go unchecked. It's about the why, as much as the how.
It really is. And for those of you listening who want to dive deeper into the history of these kinds of high-stakes engineering projects, I really recommend checking out some of our older episodes. Episode 814 on the Carrier Strike Group gives a great look at how the military handles these kinds of complex, lethal environments. And episode 793 on the engineering of survival sirens touches on how we design systems for those split-second moments where everything is on the line.
Yeah, those are both great companions to this discussion. And as always, we want to thank Daniel for sending in this prompt. It gave us a lot to think about. If you are enjoying the show and finding these deep dives valuable, we would really appreciate it if you could leave us a review on your podcast app or on Spotify. It genuinely helps other people find the show and allows us to keep doing this.
It really does. We love seeing the feedback and knowing what topics you guys are interested in. You can always find our full archive and a contact form at our website, myweirdprompts.com. We have over 900 episodes there now, covering everything from battery chemistry to the history of the steam engine.
970 episodes to be exact. It is quite the library. Alright, I think that covers the Titan. It is a somber reminder of why we do what we do and why the details matter.
They matter more than anything else at 3,800 meters. Thanks for listening to My Weird Prompts.
We will see you next time. Stay curious, but stay safe out there.
Goodbye, everyone.
So, Herman, before we wrap up completely, I was thinking about the materials again. If you were going to design a submersible today to go to those depths, but you wanted to use something other than titanium, is there anything even on the horizon?
That is the thing, Korn. Material science is advancing, but for high-pressure environments, we are still largely stuck with the classics. There are some ceramics that show promise because they are incredibly strong in compression, but they have the same problem as carbon fiber. They are brittle. If you get a tiny chip or a crack, the whole thing fails catastrophically. There was actually an experimental sub called the Deep Rover that used a thick acrylic sphere. It provided amazing views, but it was limited to about 1,000 meters because acrylic starts to deform and creep under pressure.
I remember seeing those. They look like giant fish bowls. It's incredible to think about the engineering that goes into something as simple as a window at those depths. The Titan's viewport was another point of contention, wasn't it?
Oh, absolutely. The viewport on the Titan was only certified by its manufacturer, Acrylica, to 1,300 meters. OceanGate was taking it to nearly 4,000. That is a factor of safety of less than 1. It is almost unbelievable when you say it out loud. Again, it goes back to that idea of we tested it and it didn't break, so it must be fine. But in engineering, it hasn't failed yet is not the same thing as it is safe.
Right. It's the difference between empirical evidence and structural certainty. You can survive Russian roulette 5 times in a row, but that doesn't mean the game is safe. It just means you have been lucky. And eventually, your luck runs out.
And when your luck runs out at nearly 6,000 pounds per square inch, there is no second chance. I think that is the ultimate takeaway. Engineering is the art of managing the known unknowns, and the ocean is full of them. If you don't have the humility to admit what you don't know, the environment will teach it to you in the hardest way possible.
Humility. That might be the most important engineering tool of all. All right, let's leave it there. This has been my weird prompts. We will be back soon with another exploration of the strange, the technical, and the deeply human.
See you then.
One last thing, Herman. I was thinking about our house in Jerusalem. We are a long way from the Atlantic, but the principles of good design apply everywhere, don't they? Whether it's the structural integrity of these old stone buildings, or the way we manage our own technical projects.
They really do. Physics is universal. Whether you are at the bottom of the ocean or just trying to make sure your bookshelf doesn't collapse under the weight of too many engineering textbooks. It's all about understanding the forces at play and respecting the limits of your materials.
All right, now we are really signing off. Thanks again for listening.
Take care, everyone.
Actually, Herman, I just thought of one more detail about the carbon fiber. You mentioned it was 5 inches thick. That sounds like a lot, but in the world of composite manufacturing, getting a 5-inch thick layup to be perfectly uniform without any internal voids is incredibly difficult.
You are spot on. When you are doing a layup that thick, the heat generated during the curing process, what they call the exotherm, can actually damage the resin in the center of the stack if it isn't managed perfectly. It can lead to internal stresses before the hull even sees a drop of water. It's just another layer of complexity that they were trying to brute force their way through.
It really was a house of cards. A very expensive, very dangerous house of cards. Okay, I'm done now. For real this time.
Haha, alright, Corn. Let's go get some coffee.
Oh, it's good. Bye, everyone.
Bye.
Wait, did we mention the website?
Yes, Corn. MyWeirdPrompts.com.
Right. Just making sure. Okay, see ya.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show, my